welcome to this problem walkthrough. Today, we'll be exploring the problem number 1004, max consecutive ones 3. In this session, we'll break down the problem, analyze different approaches, and guide you step by step toward crafting an optimal solution. Let's get started. In this problem, we are working with a binary array called nums, which contains only 0s and 1s. Along with this array, we are given an integer k. The task is to determine the maximum number of consecutive 1s we can achieve in the array by flipping at most k 0s to 1s. Flipping means we can choose up to k indices in the array where the element is 0 and turn those values into 1. The ultimate goal is to return the length of the longest sequence of consecutive 1s we can obtain after making these flips. For example, the input nums could look like 1, 0, 1, 1, 0, 1, and k might be 2. The output would then be an integer representing the maximum stretch of consecutive 1s we can achieve after flipping at most k zeros. To make things clearer, let's look at some examples. In the first example, the input array is 1, 1, 0, 0, 1, 1, 1, 0, 1, and k is 2. Here, we are allowed to flip up to 2 0s to 1s. If we flip the 2 0s located at indices 2 and 3, the array becomes 1, 1, 1, 1, 1, 1, 1, 0, 1. This transformation results in a maximum of 6 consecutive 1s, which is the output for this example. In another example, where the input is 0, 0, 1, 1, 0, 0, 1, and k is 1, we can flip 1, 0. By flipping to 0 at index 4, the array becomes 0, 0, 1, 1, 1, 0, 1, and the longest sequence of consecutive 1s is 3, which is the output. In the third example, we have the array 1, 0, 1, 1, 0, 1, 0, 1, and k is 3. With the ability to flip 3 0s to 1s, we can modify all 3 0s in the array. This transforms the array into 1, 1, 1, 1, 1, 1, 1, 1, resulting in a total of 8 consecutive 1s, which is the output. Now, let's consider some constraints and edge cases. The length of the array nums can be up to 100,000 elements, and each element is either 0 or 1. If k is 0, the result will simply be the length of the longest sequence of consecutive 1s in the original array because no flips can be made. On the other hand, if all elements are 0s, the result will depend on whether k is large enough to flip some or all of them. Finally, if k is larger than or equal to the number of 0s in the array, the entire array can be flipped, making the output equal to the length of the array itself. To solve this problem, we can start by considering the brute force approach. The intuition here is straightforward. We would examine every possible subarray in the binary array, count the number of zeros in each of them, and determine whether flipping those zeros within the allowed limit of k leads to the longest sequence of consecutive ones. The steps for this are simple. First, iterate over all potential starting indices of subarrays. Then, for each starting index, iterate over all possible ending indices to form subarrays. Within each subarray, count the number of zeros. If that count is less than or equal to k, calculate the subarray's length and update the maximum length we've found so far. However, while this approach is conceptually simple, it is computationally expensive. The time complexity is n squared, as we need to evaluate all subarrays, and this becomes infeasible for large arrays where n can be as large as 10 to the power of 5. Additionally, the space complexity is 1, but the high time cost makes this approach impractical for most real-world scenarios. A much more efficient solution comes from using the sliding window approach. Instead of analyzing every possible subarray, we dynamically maintain a valid window where the number of zeros flipped is at most k. The key observation here is that we can expand and shrink this window as needed, ensuring that it remains valid while also tracking the maximum length of consecutive ones. The problem then becomes one of managing this window efficiently. The steps are as follows: initialize 2 pointers, left and right, to represent the window, both starting at 0. As we expand the window by moving the right pointer, we count the number of zeros within it. If the window becomes invalid, that is, it contains more than k zeros, we shrink it by moving the left pointer until it's valid again. Throughout this process, we keep track of the maximum length of the window. The beauty of this approach is its efficiency. The time complexity is n, since each element is processed at most twice, once when expanding and once when shrinking. The space complexity is 1, making it highly suitable for large input sizes. The sliding window approach stands out as the optimal strategy for this problem. What makes it so effective is the realization that we can dynamically track the number of zeros within the window instead of recalculating this count repeatedly for every subarray. This insight allows the algorithm to run in linear time, a significant improvement over the brute force method. While the brute force approach is conceptually easier to understand, it quickly becomes impractical for larger arrays due to its quadratic time complexity. The sliding window method, on the other hand, balances efficiency with simplicity, making it the ideal choice. By focusing on maintaining a single valid window and adjusting it as needed, we ensure correctness while minimizing computational overhead. This strategy is not only efficient but also elegant in its design. The sliding window implementation reflects this optimized strategy. By using a single loop, the algorithm processes the array in just one pass, ensuring optimal performance. Each time the right pointer moves, we check whether the current element is a zero and adjust the zero count accordingly. If the number of zeros exceeds k, the left pointer moves forward to shrink the window until it becomes valid again. Throughout this process, we continuously update the maximum length of the window, which represents the answer. This simple yet powerful approach guarantees that we achieve the best possible runtime for this problem, making it both efficient and scalable. The problem we're tackling involves a binary array, nums, which contains only 0s and 1s, along with an integer k. The goal is to determine the maximum number of consecutive 1s that can be achieved by flipping at most k0s to 1s. To begin, one possible solution is the brute force approach. Here's how it works. First, we iterate over all possible subarrays of nums. To do this, we use two nested loops. The outer loop selects the starting index I of the subarray, while the inner loop selects the ending index j. For a given pair, I, j, the subarray is defined as nums, I, j plus 1. Once we have a subarray, we count the number of 0s within it. This count represents the number of flips needed to turn all elements of the subarray into 1s. If the number of 0s is less than or equal to k, we calculate the length of the subarray, which is given by j I plus 1. We then keep track of the maximum subarray length that satisfies this condition. This process is repeated for all possible subarrays to find the solution. To complete the brute force approach, we evaluate every subarray in the array and return the maximum length found. However, this method is highly inefficient, with a time complexity of n superscript 3, due to the nested loops and the traversal required to count 0s. A better solution is the sliding window technique, which reduces the time complexity to n. Here's how it works. We begin by initializing two pointers, left and right, both set to 0. These pointers define the boundaries of the current window. Additionally, we maintain a variable, 0_count, to track the number of 0s in the current window, and another variable, max_length, to store the maximum length of valid windows found so far. To expand the window, we increment the right pointer. If the element at nums, right, is 0, we increase the 0_count. This allows us to gradually include more elements into the window while keeping track of the number of flips needed to turn all 0s within the window into 1s. When expanding the window, it's possible that the 0_count exceeds k, meaning we have more 0s than we can flip. In this case, we need to shrink the window to restore validity. To do this, we increment the left pointer, which moves the left boundary of the window forward. If the element at nums, left, was a 0, we decrement the 0_count to reflect the fact that this 0 is no longer part of the window. Once the window is valid again, we calculate its length, using the formula right, left plus 1. If this length is greater than the current max_length, we update max_length to reflect the new maximum. By the end of this process, after processing all elements in the array, we return the value of max_length as the result. This method ensures that we find the longest subarray of consecutive 1s that can be achieved with at most k flips, while maintaining efficiency. The sliding window technique works because it dynamically adjusts the window size to maintain the condition 0_count equals k. This eliminates the need to recalculate from scratch for every subarray, making the algorithm much more efficient. The two-pointer approach ensures that every element is processed at most twice, once when expanding the window and once when shrinking it. When considering edge cases, the algorithm handles them efficiently. If k is 0, the result is simply the length of the longest consecutive sequence of 1s in the array. If the array contains only 0s, the result will be the smaller of k and the array's length. Finally, if the array contains only 1s, the result is the entire array's length since no flips are needed. The sliding window method uses minimal additional data structures. We rely on two pointers to define the window, a counter to track the 0s in the window, and a variable to store the maximum length found. This simplicity ensures both speed and space efficiency. Analyzing the complexity of our approaches, the brute force method has a time complexity of O n superscript 3. This is due to the nested loops iterating over all subarrays and the additional traversal to count 0s. In contrast, the sliding window technique achieves a time complexity of O n, because each element is processed at most twice, once when expanding the window and once when shrinking it. Both approaches use O1 additional space, as they do not require any extra data structures beyond simple variables. To illustrate the sliding window technique, consider an example: nums equals 1, 1, 0, 0, 1, 1, 1, 0, 1, and k equals 2. Here, we initialize left equals 0, right equals 0, 0 underscore count equals 0, and max underscore length equals 0. As we expand right to include elements from nums 0 to nums 8, we monitor 0 underscore count to ensure it doesn't exceed k. If it does, we shrink the window by moving left forward. Throughout the process, we record and update the maximum window size whenever we find a valid window. The result for this example is a maximum of 7 consecutive 1s. This implementation solves the problem using the sliding window technique, which is optimal for problems involving subarrays or substrings. Here's a breakdown of the code. 1. Initialization asterisk. Left is initialized to 0. It represents the left boundary of the sliding window. Max underscore ones is initialized to 0. This will store the maximum number of consecutive ones we can achieve. 2. Iterating over the array asterisk. We iterate through the array using a for loop, with right representing the right boundary of the sliding window. 3. Flipping zeros, decrementing k. Whenever we encounter a 0 at nums right, we decrement k because flipping a 0 consumes one of our allowed flips. 4. Adjusting the window asterisk. If k becomes negative, indicating we've used more flips than allowed, the while loop moves the left pointer to shrink the window. This process ensures k becomes non-negative again. 5. Updating the maximum asterisk. After adjusting the window, we calculate the length of the window as right, left plus 1 and update max underscore ones if this length is greater than the current value. 6. Returning the result asterisk. Once the loop completes, max underscore ones contains the length of the longest subarray of 1s, with at most k flips, and we return it. This approach has a time complexity of O n, where n is the length of the input array nums. The sliding window ensures that each element is processed at most twice, once by the right pointer and once by the left pointer. This makes the algorithm highly efficient for large input sizes. Additionally, the space complexity is O1, because no extra space is used beyond a few variables. This is the Java implementation of the max consecutive ones 3 problem from LeetCode. The logic mirrors the Python solution, using a sliding window approach to maximize the length of subarrays containing ones after flipping at most k zeros. Key differences include explicit type declarations for variables and Java's class structure. The for loop iterates over the array, and a while loop ensures the window is adjusted when the number of zeros exceeds k. The maximum length of valid subarrays is computed dynamically during traversal. To solve this problem, we use a sliding window approach. Starting with the first example, we have the array nums equals 1, 1, 0, 0, 1, 1, 1, 0, and k equals 2. The sliding window begins empty, with left initialized to 0 and max underscore 1 set to 0. At each step, we extend the window by moving right to include the current element. At right equals 0, the value is 1, so there's no need to decrement k. We update the maximum number of consecutive ones by calculating max underscore ones equals max, 0, 0 to 0 plus 1, which equals 1. The window now includes just the first element, 1. At right equals 1, the value is again 1, so k remains unchanged. We recalculate max_1s as 2, and the window expands to 1, 1. At right equals 2, we encounter a 0, so we decrement k to 1. The window becomes 1, 1, 0, and max_1s updates to 3. Then, at right equals 3, another 0 reduces k to 0. The window grows to 1, 1, 0, 0, and max_1s increases to 4. Now, as right moves to 4, we find a 1, which does not affect k since it's not a 0. The window expands to 1, 1, 0, 0, 1, and max_1s updates to 5. At right equals 5, another 1 keeps k at 0, and we include it in the window, which now spans 1, 1, 0, 0, 1, 1. The maximum consecutive ones increase to 6. At right equals 6, we encounter another 1, keeping k unchanged. The window becomes 1, 1, 0, 0, 1, 1, 1, and max_1s reaches 7. However, at right equals 7, we encounter a 0, which reduces k to -1. Since k is now negative, we need to adjust the window by moving the left pointer. As left increments from 0 to 1 and then 2, k remains -1 because the elements being removed are 1s. When left reaches 3, we remove a 0, incrementing k back to 0. The window adjusts to 0, 1, 1, 1, 0, and although the window length is shifted, max_1s remains at 7. In this example, the final output is 7, as we achieve the longest sequence of consecutive ones by flipping up to 2 zeros. Now, let's look at another example, nums equals 0, 0, 1, 1, 0, 0, with k equals 3. The initial state has left at 0, max_1s at 0, and k at 3. At right equals 0, we encounter a 0, so we decrement k to 2. The window includes 0, and max_1s updates to 1. At right equals 1, another 0 reduces k to 1, and the window becomes 0, 0, with max_1s updating to 2. At right equals 2, we find a 1, which does not affect k, and the window expands to 0, 0, 1. The maximum consecutive ones increase to 3. At right equals 3, another 1 keeps k unchanged. The window grows to 0, 0, 1, 1, and max_1s updates to 4. At right equals 4, we encounter a 0, so we decrement k to 0. The window becomes 0, 0, 1, 1, 0, and max_1s increases to 5. At right equals 5, another 0 reduces k to -1. Since k is negative, we adjust the window by moving the left pointer. As left increments from 0 to 1, we remove a 0, incrementing k back to 0. The window adjusts to 0, 1, 1, 0, 0, and max_1s remains at 5. The final output for this example is 5, as this is the longest sequence of consecutive ones we can achieve using up to 3 flips. Finally, consider the third example, nums equals 1, 1, 1, with k equals 0. Here, no flips are allowed, so we simply count the existing consecutive ones. Starting with left equals 0, max_1s equals 0, and k equals 0, we begin expanding the window. At right equals 0, the value is 1, so k remains unchanged. The window becomes 1, and max_1s updates to 1. At right equals 1, another 1 keeps k at 0. The window expands to 1, 1, and max_1s updates to 2. Finally, at right equals 2, we find another 1, and the window becomes 1, 1, 1. The maximum consecutive ones increase to 3. Since no flips were necessary, the final output is simply the length of the array, which is 3 for this example. The time complexity of this solution is O(n), where n is the length of the input array. Let's break this down step by step. First, we have the outer loop, which uses the right pointer to iterate through the array. This loop runs exactly n times, as the pointer traverses from the start to the end of the array. Next, we have the inner while loop, which adjusts the left pointer whenever the number of allowed flips, k, becomes negative. Importantly, the left pointer only moves forward, and each element in the array is processed at most once by this pointer. This means that, across all iterations of the outer loop, the total movement of the left pointer is also O(n). Finally, all other operations inside the loops, such as comparisons or updates, are constant time, or O(1). Combining these, the overall time complexity of the algorithm is O(n). Since both the right and left pointers each traverse the array at most once, the total time complexity is O(n). Now, let's analyze the space complexity. The algorithm operates with a constant amount of extra space, making the space complexity O(1). Here's why: the variables left, right, k, and max_1 store values that do not grow with the size of the input array. These variables occupy a fixed amount of memory regardless of the size of the array. Additionally, the input array itself is not modified, and no additional data structures are used to store intermediate results. As a result, the space usage remains constant, and the space complexity is O(1). To better understand the efficiency of this approach, let's compare it to a brute force solution. In a naive approach, we would generate all possible subarrays of the input array and check how many zeros in each subarray can be flipped within the limit k. Generating all subarrays would involve O(n²) operations, and counting the zeros in each subarray would take O(n) in the worst case. This results in a total time complexity of O(n³), which is highly inefficient for large inputs. In contrast, the sliding window technique optimizes the problem significantly. By maintaining a dynamic window and adjusting the pointers intelligently, the solution achieves an O(n) time complexity, as we discussed earlier, and uses only O(1) space. This improvement makes the sliding window approach both faster and more memory efficient. Now, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, the input array consists entirely of ones. Here, the k flips are never used, and the while loop does not execute. The right pointer simply traverses the array, resulting in a time complexity of O(n). In an average case, where the array contains a mix of ones and zeros, the right pointer traverses the array while the left pointer occasionally adjusts when k becomes negative. Even in this scenario, both pointers traverse the array at most once, so the time complexity remains O(n). In the worst case, the array alternates between zeros and ones. This causes frequent adjustments of the left pointer whenever a zero is encountered. Despite this, the total traversal of both pointers is still bounded by O(n), ensuring that the worst-case complexity is no worse than O(n). Finally, let's confirm the O(n) time complexity mathematically. The right pointer moves from the beginning to the end of the array, contributing O(n). The left pointer only moves forward, and each element is visited at most once by the left pointer, adding another O(n). Adding these two contributions gives a total of O(n). Since all other operations are constant time and no extra space is used, the space complexity is O(1). This combination of O(n) time and O(1) space makes the sliding window approach a highly efficient solution for this problem. When solving this problem, there are a few common mistakes to watch out for. First, failing to account for edge cases is a frequent pitfall. For instance, consider arrays where all elements are either 1 or 0. Neglecting these scenarios can lead to incorrect results or even runtime errors. To address this, always test your algorithm with edge cases, such as empty arrays, single-element arrays, or arrays with all identical values. Another mistake is relying on an inefficient brute force solution, like checking all possible subarrays with O(n³) or O(n²) complexity. These approaches are computationally expensive and often exceed time limits for larger inputs. Instead, optimize your solution with techniques like sliding window or prefix sums to achieve O(n) complexity. Lastly, mismanaging the k-flips is another common error. For example, if you forget to adjust the count of flips when moving the left pointer in the sliding window, you may overestimate the valid window size. The fix here is to ensure your sliding window logic correctly accounts for flips and maintains a valid window as you iterate through the array. Another frequent issue is not resetting pointers correctly when using a sliding window. If you update the window's left pointer too early or too late, you risk missing valid subarrays or underestimating the longest sequence. To avoid this, carefully manage pointer updates to maintain the sliding window invariant. Additionally, confusion between indices and values can lead to logical errors. For instance, mistaking an index for a value during traversal might cause incorrect calculations or results. A good practice is to double-check your loops and variable names to ensure that indices and their corresponding values are clearly distinguished. These details might seem small, but addressing them can prevent significant issues and make your code more robust. Now let's focus on insights that can help you during interviews. Mastering the sliding window technique is crucial, especially for problems involving subarrays or subsequences. You need to understand how to dynamically adjust the window size while adhering to constraints like K-flips. Being aware of edge cases is equally important. Always ask your interviewer about constraints such as array size or potential extreme cases for K. When discussing your approach, it's okay to start with a brute force solution, but make sure to quickly pivot to optimizations like sliding window, prefix sums, or even segment trees if they're applicable. Debugging as you code is also a great habit. Small test cases can help you incrementally validate your logic and catch mistakes early. Finally, be prepared to discuss trade-offs. For example, you might weigh time complexity against space complexity when comparing sliding window and prefix sum approaches. To sharpen your skills, consider exploring related problems, such as LeetCode 424, which focuses on character replacements, or LeetCode 487, which deals with a similar consecutive one scenario. Finally, let's explore some alternative approaches that you might encounter or consider. One option is the prefix sum technique. This approach simplifies calculating subarray sums, though it requires n additional space. It's especially useful in scenarios where the array is static and multiple queries need to be handled efficiently. Another method combines binary search with prefix sums. While this approach is more complex to implement, it's valuable for problems with tighter constraints where the sliding window technique may not be the best fit. Lastly, there are greedy algorithms. These can be appealing for their efficiency but might not always guarantee a correct solution. They're best suited for problems where approximate answers are acceptable and performance is critical. Each of these methods has trade-offs, so understanding their use cases and limitations will make you a more versatile problem solver. Great job completing this walkthrough. To recap, we used a sliding window approach to solve max consecutive ones 3 with optimal efficiency. Remember, mastering techniques like sliding windows will help you tackle a range of array-based problems. Thanks for watching, and don't forget to subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!